Let me start on this calculus, whether it should be Ganit or mathematics. So let me give you a quick overview. The aerospace department, aerial view. So Ganit, first of all, is not the same thing as mathematics. I think it's a common translation, but it is important to discriminate between the two. I will tell you what are the differences. There are a large number of differences, but this is important. Second thing is we invented calculus, and this was over a prolonged period, about 1000 years, starting from Aryabhata and going on to Neelakant. Europeans stole it, because they didn't acknowledge. Unlike, let us say, Indian arithmetic, which went to Betar, Hikma and Mudar, they stole it. But, and this is the critical point, they developed it, they stole it, but they didn't understand it. They didn't understand it. And then, to fit with their cultural framework, they converted it from Ganit to mathematics. That is what we teach today, calculus with limits, real line, derivative, so on. This was packed with the false history, Newton and Leibniz invented, and declared to be superior. Still people who do it. So rigorous. It was returned to India through colonial education. Now the point I wish to state, something extremely sad. How were we taken for a ride like this for 200 years? Nobody cross-checked it. Not a single person cross-checked it. Some people are fighting and so on, but they didn't cross-check the Western history, that it is completely false. And they didn't cross-check the claim that math is superior to Ganit. Why not? See, this was a contrary. And it's one thing that a couple of individuals or a few hundred individuals fall prey to it. It's quite another thing that you have a billion people, a nation, a billion people falling prey to it for 2 centuries. Just accepted it. Science in practice, what is it you want? You want community opinion, you want impact parameter, you want to publish papers, you want impact parameter, you want citation index and so on. And so that is all controlled. The community, the dominant elements in the community are Western scientists who have huge amount of funds, and the result is that it becomes blind faith in the West. Unfortunately, I expose both the false history, Western history of calculus, and the false claim that math is superior to Ganit. So what does one expect? One expects that there would be a lively debate on it. Nobody debates. They evade debate. I have been asking for a debate. I have offered a prize of 2 lakh rupees. For example, for the existence of Euclid, nobody dares to take up the prize, and nobody removes it from the textbooks. That is dishonest. Right? It should be either you offered a challenge, take it up. Don't take it up. Be honest and say that the history that we have, that Euclid was the father of mathematics, is complete nonsense. Not the slightest evidence for it. So they just say, well, what are you talking about? Okay, something non-standard analysis, non-Archimedean arithmetic, we don't understand. What do we understand? Get a certificate of approval from the West, that we understand. Well, that is what colonized academics did. Colonial education did, it created clerks. You understand what our masters say, they control the money. That's not a very good idea. Because science is about thinking for yourself. It's about examining evidence. And we need to do that here and now and not say that somebody else should tell us. It's just another form of faith. Alright. So the consequence, what does it matter? It's not just about glory. There are very important consequences. One of them is that calculus as math has hindered science. The point I made is that Newtonian physics failed just for that reason. And the second thing is that it makes math atrociously difficult. In fact, as Russell bragged, that's the chief advantage of formal mathematics, that it makes math difficult. To prove 2 plus 2 equal to 4, he takes 378 pages in his Principia. 378 pages for such a simple thing. Why do you need it? So it makes math difficult on purpose, extraordinarily difficult, and that's why people leave it. If we return to calculus as Ganit, what happens? We have the advantage that it makes math very easy. You can do that calculus text of 1400 pages, can be done in 5 days, as I have demonstrated. It suits all practical applications of the calculus, which are, for example, done today on a computer. And it also suits advanced applications better than the existing university calculus, as one might call it, or the Schwartz theory of distributions and so on. Okay, so the second point I would like to say is that this is a general story, not something which concerns calculus alone. It concerns most of present day school math. It means arithmetic, algebra, trigonometry, probability, all of which originated in India and was transmitted to Europe and given back through colonial education. Why am I telling you this story? Because it's easier to understand. Calculus is a little difficult. You're talking about limits and talking about real numbers and talking about Schwartz distributions and whatnot. It becomes a little difficult for many people to understand. In the case of arithmetic, it's an easy story to understand. So I want to establish that story as an analogy. Once that is clear, then you can go to the case of the calculus. It's a very simple thing, similar to that. So let's take the case of arithmetic. That it originated as Ganit, was transmitted to Europe, where it was misunderstood, returned as math, pianos, axioms, so on and so forth. So it's an easier story. Now I want to start with this issue, whether anybody can write 1788 in Roman numerals.
I've luckily forgotten how to write.
Okay. Anybody else? So it's not a rhetorical question. The point is that it is very difficult. If you try to write it, it's extremely difficult. Right? This is the answer. And the point is it needs 12 symbols instead of 4. So, very inefficient system just to write numbers. Inferior system, the Roman and Greek way of doing things. How about 10 raised to 53? Anybody wants to try 10 raised to 53? Now you have such a number in Indian tradition. Because it has a superior decimal place value system, so names up to 10 to the power 12 are found in the Yajurveda. 17.2, that's the reference. If you want it, I have the text, I can show you. Deduction is found in the Buddhist Lalit Vistar Sutta. 10 raised to 53, their names, where the Buddha resides, all these names, powers, you find even larger numbers. So why? Well, this is the Yajurveda. 17.2, so as you see, Ekacha, Dashacha, Dashacha, Shatamcha, and so on. The point is that such large numbers arose because there was a very efficient decimal place value system which could represent these numbers, which could generate these numbers. And that led to efficient arithmetic. And what is that efficient arithmetic? It is just what you learn in school today. Your methods of addition, subtraction, division, multiplication, you might think it is trivial. It is not trivial. Nobody else had it. Egyptians had difficulty with it. They had the best sort of arithmetic outside of India. I don't know about the Maya. I don't understand their language. But certainly nobody in Europe had it, as you just saw. It's called Patiganit, slate arithmetic and so on. It's found in various texts like Brahma's Siddhant, or Patiganit Rigor, Ganita Sangra, Mahavir, Gilavati of Vasco, and so on. The Arabs recognized the efficiency, even the Greeks recognized, Civilus Sebot, Greek bishop, accepted the efficiency of Indian arithmetic. It was imported in the Vedal Lipa. And then, as you know, Al-Khwarizmi wrote a book on it called Hisab al-Hind. We get you credit. We share knowledge, not a problem. It's when people steal and don't recognize that it becomes a problem, that it becomes a strategy to obtain power by telling lies through false history. So this text was translated into Latin, and Polyphony's Latin name was algorithmus. That's why we call them algorithms for addition, subtraction, and so on. From his name. That was the European practice. Now, why did Europeans import Indian arithmetic? Because their own arithmetic was inferior, it was deficient. They were using Roman arithmetic right up to the 16th century. Certainly up to the 10th century, they had not heard of any other kind of arithmetic. And that inferiority is very clear if you try to do some operations, simple operations like this. Now don't convert it to decimals and then do the calculation and then convert it back. That's not the way to do it. What you have to do is that you do it the way the Romans did it. What did they do? Very complicated process. They did it by repeated addition. Alright, so can we add these? Can you add these two? Once? How long would it take? Just think of it. So you see they used counters. That was their technique. So you'll have a counter for 10, a counter for 50, counter for 5, just like coins. Okay? They used an abacus. And there was a big quarrel for 5 centuries in Europe between abacus and algorithms. So you write it out in its full form, no abbreviations allowed. Then you use counter, 1 coin each for each of those, put them all together. Then you simplify. Right? So you have 7 1s that will give you 1 V and then 2 1s left out. The 3 V's will give you 1 X and 1 V left out. The 5 X's will give you 1 L and the 2 L's will give you 1 C. And so the sum is that much. So it's a very long process. Anybody could do it mentally. Any child can do it mentally. This sum is so trivial. Now if it takes you so long to do it once, if you have to do it 37 times or whatever is the number I have written there, 29 times, what will happen? So it takes a very long time even to do simple sums. That was the efficiency of Indian arithmetic, that you can do this in a jiffy. Alright, so you don't want to spend so much time. I give it this as an exercise to some of my students, they protest when it was too hard. So it was inefficient and it was inferior, and that is why they got a superior system. That is what everybody does, more practical system. But that inefficiency is not a trivial matter. All the stories they have heard about what Greeks did, every book in science will begin with Greeks did this, Greeks did that. How could they do science if they didn't have arithmetic? That itself should tell you this is robust, non-textual evidence. You have never seen the text. Has anyone of you seen an original Greek manuscript? In fact, they don't exist. Wikipedia will tell you long stories about them. Don't believe it. After that, it will say very little is known. And then what is that little that is known? It will say some 5th century commentator will mention. But where do you know about the 5th century commentator? From a 13th century text. We are all talking about texts from which come 1500 years after the source. They are absolutely not credible. If you accept that, then anything I say now can be attributed to 100 years ago. It would be make nonsense of history, which is what Greek history is, which is what Western history of science is about the Greeks. So it is compelling non-textual evidence against these wide and exaggerated claims of Greek scientific achievement. I gave you an example. Euclid did not exist. There is no evidence of Pythagoras. There is no evidence that he proved his theorem, and so on. A long list of it. And this was done deliberately for political purposes, first by crusading historians, then by racist historians, then by colonial historians. It's all based on late texts and wide interpretations of those texts. So I have a book on that, little booklet. So you could take a look at that. It is available for free if you want a PDF. It's on the Multiversity site. And it's also available in Hindi. It's for 40 rupees or something like that. And in Farsi if you like to read Farsi. So, because Greek and Roman arithmetic was inferior, therefore efficient in transport. That's what we look for efficient methods. First it went via Arabs in Cordoba. That was around the 10th century. Then it went through Florentine merchants because it gave a comparative advantage in commerce. So, important thing to note is India did not contribute just zero. False claim, India contributed efficient arithmetic West does not like to tell this part of this. So I have an epistemic test, how to catch students who cheat. The exam, they copy from each other. Call them, ask them some questions. Those who copy don't understand. They can write it. Writing, you can hide your ignorance. In speaking, you cannot hide your ignorance. You can write and claim, I have written so many papers and so on and so forth. You ask a few questions and then you know who has actually written. Alright. So this is what happens. So what happens is when people copy, see in some cases known as mass copying. Even when there is mass copying, if you examine, there will be errors in each individual errors in each answer sheet, even when the answer has been dictated. So there is misunderstanding, and this misunderstanding of Indian arithmetic methods persisted for centuries in the West. And this story has been suppressed. Those guys didn't understand it, they struggled and struggled. This is arithmetic I am talking about. I am not come to calculus yet, but in the case of arithmetic, it's easy to understand. So this story is told today by the very words like Arabic numerals, like the word zero, and so on, like the word sign, like the word third, which are in current use. Those very words tell you the story of lack of understanding in the West. So let's take Arabic numerals. So first when Indian arithmetic went, as I said, first went to Baghdad. From Baghdad it went to Cordoba, from the Abbasid Khilafat to the Umayyad Khilafat, and from there it was imported into Christian Europe. So he was accustomed to Roman numerals. He was a very learned man. So learned, he is portrayed as a black magician in Christian art. And he wrote a text on the abacus, most learned man then. He thought that arithmetic requires an abacus, that's how he did it. He couldn't conceive of the possibility of arithmetic which is done differently. And so what did he do? He got a special abacus constructed for these Arabic numerals. Basically what was the error? He thought that the efficiency of the arithmetic comes from some magic in the shape of the numerals. He understood the place value system. And that's why you have the term Arabic numerals. He understood the place value system. This is from a book in 976 CE when the Arabic numerals first came into Christian Europe. As you see, he has got a place value 1, 10, 100 and so on. So he understands the place value system, but he does not understand how you use algorithms for efficient arithmetic. This is the representation, but not the algorithms, not how the efficiency comes about, because he is bound by his cultural idea that arithmetic requires an abacus. Let's take the word zero. Where does zero come from? Zipr. Zipr, Cipr or Cipher, which is a code. Mysterious code. What is mysterious about the very word means that? What is mysterious about it? So the mysterious thing is that Roman numerals are additive, they are counters, right? So 12 means say 10 plus 1 plus 1. If you have the place value system, it's not additive. 120 does not mean 1 plus 2 plus 0. So people complain. Florentine merchants particularly complain. What is this? You sign a contract and somebody puts any number of zeros and then the contract becomes 10 times, 100 times, 1,000 times. This is cheating. Something very mysterious, something very wrong with these numerals. Let's be suspicious about them. So they passed a law. Florence passed a law in the 13th century. If you are going to use these numerals, they are outlawed. At least you have to write by hand. You still use that? Why do you write by hand? You don't trust the numbers. Roman numerals you can only add a little bit at the end, maybe 3 you can add that. Nobody minded. Here you are adding, doubling time, making the thing 10 times. So ultimately Indian techniques of arithmetic were introduced as practical mathematics in the Jesuit syllabus by Christoph Clavius, 1570 about. So that is at least as long as it persisted, the confusion. So 976 to 1672. So you can see it is about a very long period. In fact, it persisted after that because there were only some Jesuits who learned about it. So many other people didn't learn about it. So the British Parliament burnt down on that. I'll tell you that story some other time. Because they were still using this abacus and they burned it. So once more, the summary that India did not contribute only zero. It was efficient arithmetic that efficient arithmetic was transmitted and replaced efficient Greco-Roman arithmetic. And the important point is that Europeans misunderstood it. They took a long time to understand it, and that confusion persisted for more than 600 years. The story of trigonometry is similar. I'll just give you a very brief account. So again, it originated, traveled perhaps, was imported to the West in a different manner by the Toledo translation. This was during the Crusades when the Toledo library was captured, and it was decided to mass translate the books in it to Latin instead of burning them as was earlier the practice of the church. So around 1125 they started mass translating those texts from Arabic to Latin. And translators didn't know mathematics, they didn't know Arabic, so there were intermediate translators, Jews from those Arabs who translated into an intermediate Romance language from which the official translator translated. So there was going to be a lot of confusion. Word sign, if you check out the Oxford English Dictionary, it will tell you its etymology. It comes from the Arabic jayb, meaning pocket. What's the connection? Sign functions and the pocket. So the connection is as follows, that the J was a misreading for jiba, because both were written as a consonantal skeleton, just as you write in SMS, SHD, should, so the vowels and so on. So it was written as a consonantal skeleton, without uttars, so not common at that time. And jiba was from the Sanskrit ja or jiva, meaning God. So this was the wrong translation. Of course, wrong translations happen all the time. Point is, there was a conceptual misunderstanding. That's what I am talking about. So the conceptual mistake is that the sign is half chord, or the ja, as Aryabhata calls it. If I complete this ja, it's chord. It relates to a circle. It's a circular function. It doesn't relate to a triangle opposite side by hypotenuse as it is defined for people. There is a conceptual mistake in the very term trigonometry. It's not about measuring triangles, it's about measuring circles. That's what people are trying to do. And in all Indian texts, this is always discussed in the chapter on the circle. So, important thing is the circle is a curved line. It's not a straight line. And how do you learn geometry today? You learn it using a compass box. Does it have any instrument to measure curved lines? Doesn't have. People get conceptually confused even by the simple things like notion of an angle. How do you define an angle? Please tell me. It's a good question, very elementary mathematical question. It's like an answer. What is an angle?
Length of facade of prism.
Yes, but that's a curved line. How is it defined in NCERT text? It's defined as something between two straight lines. It's actually the length of a curved line. How do you measure the curved line in the compass box? There is no instrument. You measure it with a protractor. Measure it with a protractor, but how does the size, supposing I change the size of the protractor, will my angle measure change? If it won't change, why not? Because you are using a property of the circle in an essential way just to define the notion of an angle. Most people are confused about it. So, can you define it axiomatically? That is when in fact the calculus began. What the length of your guess is? You have an axiomatic calculus? 1 degree?
1/360th of a circle.
1/360th of a circle. Yeah, so long as you are measuring the of the circumference. Yeah. Right? If you are doing it in radians, you will do it differently. So you are measuring the length of a curved arc. How do you measure the length of a curved arc axiomatically? That's the question. That other question was there earlier. How do you measure, how do you define the length of a curved arc or a curved line axiomatically?
Approximation by.
So if you have approximation, then there is where you start diverging between Ganita and mathematics. So if you accept approximation, you are doing engineering or you are doing Ganita. You are not doing mathematics because you want something perfect in the case of math. That's the problem. Alright? So these are all issues which arise. And in the Indian Shukla Sutra, you had a flexible string. And with the flexible string, you can obviously measure curved lines and arcs. And in fact, you can use that string to replace the entire compass box. As I have argued, you can measure it, you can straighten it, measure straight lines. And therefore you can calculate the number called pi. And this is where calculus begins. So let me shift to that. That the story of that is similar to that of arithmetic and trigonometry. Developed in India, stole it, Europeans stole it and claimed it. But conceptually misunderstood. Just as it happened in the case of trigonometry or it happened in the case of arithmetic, the conceptually misunderstood. And the story is told in my book, Cultural Foundations of Mathematics. So this effort started in the 1990s. 1990 in fact. A group of intellectuals got together, said that let us tell our own story. We don't want the story that has been told about us by the colonial masters. And this was a very influential group, lot of people there, Krishna, D.P. Chattopadhyay, Vedra Bakshi, all sorts of people, anybody you can name was there. So, this story is told, that's 500-page book. I can't tell you the entire story, I'll try to go through it fast. The point is that Aryabhata improved the value of pi to Shukla Sutra. And its value is stated in this, Ganita 10. So this was the value that he stated it like this because it had to be stated in verse. And there is a meter in verse and therefore it is stated in a roundabout way. So 100 plus 4 multiplied by 8. And this is not, he is not giving the value of pi, he is giving the measure of the circumference. And what is he giving? He is giving an asanna measure, near value, an approximate value, he is stating it. Just as the Shukla Sutra will state an approximate value, this is what he is stating. So this question of approximation has come in because when you are trying to define a curved line, how do you define it? At the length of a curved line, how do you define it? That's the question. So you can't get a perfect value. And this value of pi is repeated by other polynomials. And also by Simon Stevin, the 16th century navigational theorist. In Europe, who introduced, as you know, the decimal, Europe to the decimal place value system. So, another strange, something which I find strange, which I find a little troubling. That Aryabhata gave these values, he improved on the prevalent sine table, which involved 6 values of the sort which you study now, 15 degrees apart. Tested from today. Why don't we go back to what Aryabhata did? Because there was a very dramatic departure at that point. Those values, they involve some symmetry, you can get them geometrically. You can't do geometry where there is no symmetry. So, difficult to calculate sine of 1 degree. This was one of the questions my son asked me. You have to explain how to do it. You can't do it with triangles. So he made a striking departure. He did not do it geometrically, he did it numerically. He calculated these 24 values, which are 3.75 degrees apart. So our trigonometric texts do, they are still 1500 years behind the times. Most unfortunate. Because you have not graduated to that, we are still stuck with the pre-Aryabhata values. So there was a striking shift because they solved what you might call difference equations, which are only metaphysically different from differential equations. Because every difference equation that you solve, every differential equation that you solve, most of them, except for a very few simple things where you can write down a formula, writing down a formula doesn't mean much. Ultimately, when you want to calculate it, you have to calculate it. You have to use the difference equation. That's how you do it on computers all the time. So there is not, in practical terms, there is no difference. He solved them in a very simple way. Use linear interpolation or what he called the rule of 3. And today that is wrongly called Euler's method. Euler was of course aware, he studied Indian texts. He wrote an article on the Indian calendar and so on. Studied Indian astronomical texts, but it was a habit that Westerners never, especially during the time of the Inquisition, they did not acknowledge, because if you acknowledge the non-Christian source, you would be killed. That is how Copernicus became a revolutionary. He did not acknowledge the non-Christian source, which was the initiator of Damish. He did nothing original, just translated it from Greek to Latin. Calling him a great revolutionary. All Western history is like that. A whole lot of it. Right? Even like you come to the time of Edison or you come to the time of more recent times. I don't want to go into more recent times. So the important thing is that he stated only the sign differences, which are later called khandajas. And they can be directly used to interpolate and calculate any sign value there. What we need is the difference, the rate of change. So this is an exercise I do in class, very easy, just linear interpolation. So this is what he stated. This is how he stated his sign values using his notation, which is a very compact notation, but difficult to write poetry. As you can see, he tried monkey, bucky, 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 and so on. So this is the translation. I won't go into his notation. It is given in my book. You can check it out. Given in many other books, Shukla and Sharma, for example. Slight change in my translation and this. So he is giving this. What is it? Have a circumference of the circle is assumed to be this. So he is doing calculations accurate to the minute. And then later on the accuracy develops. People do it accurate to the second, and people do it accurate to the thirds. It takes 1,000 years. So, point I want to emphasize is that he was using a difference equation and not an algebraic equation. Because many of our even our leading scholars have wrongly tried to understand things in terms of algebraic equations. It cannot be so understood. Right? So I will just skip through it because it will take you some time to understand. I just wanted to flag this point. And there is a problem of translation here. Why runam? What does why runam mean? Does it mean the second of the first differences or the second difference? There is a little issue. But anyway, second differences were used by Brahma group and so on. For more accurate interpretations, quadratic interpretations. So this is the idea, that this is the rule that he does, and he is doing it accurate to minutes. And I already mentioned that. So this is the key point, that it cannot be used as an algebraic equation. If you use it as an algebraic equation, you will get all the wrong values. And it is later corrected by Neelakant, because Neelakant is doing the calculation accurate to the thirds. And so this is the calculation I will carry out. You can't do it, you will get a wrong value in every case if you use it as an algebraic. So the other part is, it's a non-terminating process. Making infinity. How do you handle infinity? That's the question. That is where there is a very sharp division between Ganita and mathematics. Any number I want to write like pi, it's an infinite non-terminating series. And how do I handle such a thing? Do I handle it with metaphysics, with the metaphysics of eternity, or do I handle it in some practical way? That's the issue. That is true also for other algorithms like square root of 2 which are not terminating. Aryabhata has an algorithm for that. So this process developed, Aryabhata's process developed across 1,000 years. Those values were made at precise to the second by Vateshwar. Before that, people had already tried in Kerala to get them precise to the third, Govindaswamy. It was achieved by Madhav in the 14th century. And he extended this recursive process to an infinite series. So you have this gradually increasing precision in the values of pi, which tells you about the progress. So Bhaskar 1 will say 3438 minutes, and Vateshwar will go to seconds, 3437 minutes, 44 seconds, and then later it will go to thirds. Devo Vishwastharit Raju. So it's a cut-up system, reverse order. I don't want to go into all those details because I want to tell you a bigger story. In contrast, calculus was immaculately conceived. 1582, Simon Sevin introduces decimal place value system. Suddenly you have Kepler coming up with some calculus, Cavalieri coming up with something, Galileo coming up with something, Fermat, Pascal coming up with something, all of a sudden, all immaculate concepts. So when you have further values of pi, Neelakant, this is called Kerala school, that is wrong terminology. They call themselves Aryabhata school. And it's important to understand because Aryabhata was a person of the lowest caste, as the name indicates, and Neelakant, Somasutram, was the highest caste Brahmin. And he was a disciple of Aryabhata, he is writing Aryabhata Bhashya. So need to keep these realistic factors into account. And it's not Kerala school, they thought of themselves as Aryabhata school in Kerala, because Aryabhata was from Patna. You don't see the connection, there is a big problem. We should not get into this kind of chauvinism. So the all India effort as far as one can see. So he gave a very precise value, which comes out to be, wrong only in the 12th or 13th decimal places. Slide. And then he also gave a more accurate sign table, because Aryabhata's sign table was accurate to the first, this is accurate to the thirds. This is what it looks like. Shreshthanam, Varishtanam, Madhurya, Bhavna, and so on. So what does it mean? It means these numbers in reverse hexadecimal Katapyadi system. So it is Kala, Vikala, Tatpara, that's first, second, third. Minutes, seconds, third. So that is what they stand for. And that's the accuracy, as you can see, it's very highly accurate across the entire quadrant. It's not so easy to do with a so-called Taylor series expansion. Later it was. So I won't give you that exact infinite series and what all that was done, because again my point is to point out a bigger story of what happened. So first thing you have to ask is, why was so much precision needed? You saw, very highly precise, and it is growing over 1,000 years. So why is it needed? There has to be some need for it. So one need came from astronomy. Why was astronomy important? So it was needed for the two key means of wealth in India. What were the two key means of wealth? Agriculture and foreign trade. That was traditionally, those were traditionally the two key means of wealth. So for overseas trade, you need a good system of navigation. A good system of navigation, you need precise sign values, for example, to calculate the size of the earth, which was not calculated in Europe until the 17th century, 1672. And for agriculture, you need a good calendar which tells you the time of the monsoon. Very important. We have Sawan and Bhadra, which tells you the time of the monsoon. There is no such thing in the Gregorian calendar. Because it has based on bad astronomy, plus there were no seasonality. So you can see my presentation on that separately. It's a separate topic. Tale of two calendars. If you Google, you should get the video, you should get the articles and so on. It's a very bad unscientific calendar. If we use, we say we have scientific temper. Why don't we have a scientific calendar? Why do we have this unscientific calendar? This is a sign of our colonial domination. We just took whatever those guys had. We didn't ask whether it is better, whether we have something better. We have something better, our calendar is much better. Keeps track of the phases of the moon. You don't have months of varying dates, 28, 29, 30, 31 days. Anyway, straight to the topic. That's a separate topic. I have a video on that. I have a presentation on that, written up on it. Please take a look at how in the past decade various things went wrong according to the Gregorian calendar, came out right on the traditional calendar. But they were needed. I hope the point is clear. They were needed for the two key means of wealth, namely agriculture and overseas trade. You also needed to set arctangent values. There is a series, infinite series for arctangents. You want to determine the local latitude in the shadow of a neomon. So this is all discussed in my book. Or you want to determine it from solar altitude at noon, which also needs a correct determination of equinox, which was not there in the Roman calendar prior to the Gregorian reform. It's not there even now because the equinox is right longer than average, not precise. So Maya got it right. Chichen Itza gives a striking demonstration of how to measure equinox. Instead of pyramid is an egg. Anyway, you also need to determine the size of the earth, which is what Europeans did not do. Once you do that, then you can determine longitude. Because they did not have the size of the earth, they could not determine longitude at sea. They were, of course, poor Europeans at that time. They came to India to trade to earn money. Just as Syrians are now going to Europe. They came like that. They used to die by the hundreds and thousands. 1/3 of the people who came to India died. So the ships going back used to be much less, they were not crowded. And they were navigationally challenged. Their dreams of wealth depended on a good system of navigation. If a ship sinks, everything gone. And what was their navigation? Columbus, he mistook Cuba or China. You think of it, how bad he was. And then he blamed the instrument. The instrument is broken. How can it be broken if it has only one moving part? And that is a string with a bob at the end of it. Vasco da Gama couldn't determine. He had an Indian navigator. Bring him from Melinde. Came to Melinde by creeping around the coast. Could not get across the sea. So Indian navigator, maybe Kanak, maybe Kana brought him from, because there was an organized trade going back 5,000 years. And he recorded, you see, what did he understand of navigation? He said the pilot was telling the distance by his teeth. How deep? Again, one of those translation, howlers. Because the navigator must have told him, he calls him pilot, see, derogate. The navigator must have told him he is looking at the pole star. He used an instrument called the Kamar. I have a separate article on that in the book, maybe I'll tell you the story later. This Kamar uses the pole star for navigation. And you must have the word for pole star, you see these people, Mapilas, they use a peculiar language called Arabic Malayalam. And so the Malayalam word for it is cow, which is also the word for teeth. The instrument is held between the teeth when I want to measure the angular elevation of the pole star. So he said, pilot was telling the instrument by his teeth, and then he said, I will take it back. More misunderstanding. He said he will get the scale graduated in inches. It's actually a harmonic scale, right? The roads in a flute. You cannot graduate it in inches. Inches is a measure of linear scale. He didn't understand that point. And then of course they copied it and so on. Okay, so how was the campus transmitted? We know that, see, when the church is successful in something, it repeats that. So it was successful in the Toledo translation, because Toledo translations were repeated in Cochin. The texts were mass translated from Sanskrit to Latin and sent back to Europe. And where there they had Jews and Mozarabs as intermediaries, here they had the local Syrian Christians as intermediaries, and so on. Long story. So it solved the problem, sine table solved the problems of loxodromes. And it solved the problem of latitude determination. What is loxodrome? Loxodrome is a curved line. If you travel in a straight line, according to let us say 2 stars, stellar one line, 2 stars are joined, you follow that. Or you follow a set course according to your compass. You will not move in a straight line on the surface of the earth because it is curved. You will spiral towards the poles unless you are going in the cardinal directions. So these guys were puzzled. They didn't know what to do. It was the biggest problem and it was solved by the Mercator chart. Another story, another time, but that's a problem that was solved. And the latitude problem was solved, the longitude problem was not solved. Well, the Gregorian calendar reform was part of the way of solving the latitude problem in 1582. It used inputs from India. And it did not use any fresh empirical evidence. That is very clear from the fact that Protestants did not accept it. Newton thought he was born on Christmas Day. He was the leading scientist of the time, right? He did not accept that reform. It was accepted by Protestants only in 1752. So here is the primary source. Matteo Ricci, who was the favorite student of Christoph Claudius, who carried out the Gregorian reform. This is his handwritten source. As you can see, he mentions here that he is looking for an honorable move or an intelligent Brahmin to tell him about Indian methods of timekeeping. Difficult to get these sources because the Jesuit library in Rome is closed. They don't give you everything. And in Vatican, if you want, it's very expensive. Anyway, I bought it. Cost a lot of money. So here. So European navigational problem was not solved because Columbus underestimated the size of the earth. He wanted to turn it. So how to make the project seem more likely? Now Claudius, author of the Gregorian Reform, also published Mother Sine Table, 1608, accurate to 10 decimal place precision. If you knew so much trigonometry, you would be able to calculate the size of the earth. Could not do it. Right. So easy. And they could not solve the longitude problem. So these are my students in Al-Bukhari University, whom I took to measure the size of the earth, just to teach them how simple and easy it is. Just measure the angle of the dip on equinox, And that is how Fallibility records it. His measure is very accurate. When he comes to India, he does this. And this is what they are doing at the observatory just after sunset. That's a photo just after sunset. So European navigational problem persisted until the 18th century. Various governments offered big prizes. Last was the British Board of Longitude, 1711. And of course the French Royal Academy, the Royal Society, etc. was set up for the purpose of solving the navigational problem. So these things are very important. They have immense practical value so far as Europe was concerned. These sign values, you think, oh, what is it? Today you have to keep clock or another, say, oh, what is it? Just did some trigonometry. But it was the major challenge at that point of time related to navigation. And they failed to understand, because they involved infinite series. Here is where the problem comes up. They failed to understand the Indian method of summing infinite series. So finite geometric series were there. I showed you one in the Yajurveda. Infinite geometric series had already appeared in India by the 14th, 15th century. You find it in Nilakant. So Aryabhata, he gives a statement how to sum an infinite geometric series. That's the first formula. Nobody else had a formula at that time. Obviously, nobody else knew about infinite series. So this is the standard formula that you learn in a slightly different form. Instead of common ratio, you think common divisor and so on. And the number pi requires an infinite series. So for calculating sign values, for doing all this, you needed, mind you, I am saying sign values to mean all the circular functions. I am not saying trigonometric value because I just told you it's a wrong word. So the so-called Leibniz series is found in the 16th century. This is a published text. Published critically annotated text. Alright, not something I am drawing from a hat. So you can check it out very easily. It's a critical annotation done by one of our best scholars, the late K.V. Sun. So it's a very simple series, except that it converges very slowly. Once more it is computation of the circumference. And today you would write it like this. Very slowly convergent series, as you will discuss it today. The point is, what is meant by the sum of the infinite series? And this was the problem. It baffled Western thinkers, baffled Descartes, baffled Galileo, Newton, Berkeley. Why? Because they wanted to do the infinite sum perfectly. Don't do to say pi is 3.14 or 3.1415. Want the perfect answer. How do you perfectly sum an infinite number of terms? So Descartes declared the ratio of curved and straight lines is beyond the capacity of the human mind. Look at this pompous declaration. He writes that. And the Churva Sutra, you are able to do it, and this was taught to children as part of the routine syllabus. This is how you measure curved lines, this is how you measure straight lines, straight out, and you can do the ratio so easy. So, see, there is a problem. And the problem is not a practical problem, it is some metaphysical problem that is involved. And that metaphysical difficulty is what we have to understand, whether it is at all relevant to us. If you are doing mathematics for its practical value, it's done that way. So, just that metaphysics is what needs to be. We already saw that the compass box does not have that. It's a ritual thing, ritualistic thing. Set squares, what did you use set squares for? Tell me honestly. Just copy it. Solve the external like that. Ritually do it like our lawyers wear the bow tie and say your honor, and say you copy the medievalism, that is the right thing. So it just blindly accepted everything. And we did not make a critical evaluation. Is this suitable for us? Is this of any value? What should we do? What is of value? If something has practical value, by all means take it. No problem. If it is not of practical value, why do you take it? That is the problem. Right? If you wear a suit in the heat in Delhi summer, that is not of practical value. There is something wrong with it. Anyway, this is Indian rope trick is something there. So for practical purposes, you can use this. If you don't like it, you can go to a billion decimal places or whatever precision you want. You can't have perfection. something will be left out. Some very tiny thing about which you don't care, which has no practical consequences, but it will never will be left out. So that's the problem. And so Descartes thought that you have to physically sum, it's a charitable interpretation. So he thought that you have to physically sum the infinity. You are going to carry out each sum at a time that is going to take an infinite amount of time. It's a super task, only God can do it, human beings can't. That's all. Now the earliest Shukla Sutra had a different attitude, a very simple practical attitude when it calculated the value of pi, because it could do that, it could measure the curve time empirically, said that it is non-eternal knowledge and it is imperfect. This is explicitly stated. Savisesha, which means with an offset, with a remainder. Sanitya means anitya, sa anitya. So it is non-eternal. And which is a striking contrast. Because the belief in perfection, am I taking too long?
No.
Yeah? Okay. So this is a striking contrast because Westerners believe that mathematics contains eternal truths. Certain truths, eternal truths, a special kind of truth. And therefore it must be perfect because eternity, any imperfection will show up. Eternal amount of time to find out, eventually find out. But the question is, why should mathematics be perfect and eternal knowledge? Why should I believe that? Just because somebody said so. I am using mathematics for its practical purposes. I use it all the time. I don't need perfection if I am measuring something, engineering calculation, alright, engineering measurement, it's fine. Why do I need that perfection? Why do I need that claim of eternal knowledge? That is tied to religious beliefs. That practically useful knowledge, I understand. Perfect knowledge, eternal knowledge, I don't understand. So it's linked to religious beliefs. What are those religious beliefs? Very complex story, long story. Look at Plato. Plato to Prof is a distance of 1,000 years, almost 800 years. The very word mathematics, where does it derive from? Mathesis. Don't believe Wikipedia when it says mathema. They've changed religion to science. It's a false statement. Look at your at least something like Oxford English Dictionary, it will give you an honest account of mathesis. Or look at the original sources of Prof. He'll tell you mathematics derives from mathesis. Don't believe secondary and tertiary sources like Wikipedia. So what does Plato say? Mathesis means learning. What is learning? All learning is recollection. That is the Platonic formula. Recollection of what? Recollection of the eternal ideas in the soul. The soul goes through several lives. And by using mathematics, you arouse the soul and make it recollect its previous life, the knowledge of its previous life. This is in Plato Meno. It's a famous story of Socrates and the slave boy, where Socrates demonstrates that the slave boy has an innate knowledge of mathematics and then concludes that he has proved the existence of the soul. And by mathematics, probably why not geography? Doesn't do the same thing because it was believed that mathematics contains eternal truths and therefore arouses the eternal soul by sympathetic magic, like arouses life. So that was the idea. And you can see my book on that, how and why the church in mathematics and Christianity across two religious wars, that there was a spiritual mathematics which was turned into something called rational mathematics which later became common. So all based on mythology. All based on mythology and various kinds of politically convenient religious beliefs. So this is the book, and this by the way is Euclid, black woman not a white man, as is shown in the text. So maybe you can take a look. And let me go on to this question of imperfection, perfection that we have. Because Westerners believe man to be perfect, and that is what we saw was Descartes' difficulty. Also Berkeley's difficulty. When he wrote against Newton wrote all sorts of things against the church. He was a very devout Christian. And he hated the church. He wrote an abusive 7-volume history of the church. So when he died and it came out, these things came out, then they have been suppressed after. Immediately suppressed, they remain suppressed. So Berkeley found that out. So he wrote against an infidel mathematician. He argued against him. And he stated this point: the minutest errors are not to be neglected in mathematics. For practical purposes, the therefore he objected to Newton's theory of fluxions and so on. So this is one difference between Ganita and math, that math involves a religious delusion that there are eternal truths and perfect knowledge. Which delusion we have solved. It's solved, we accept it just because Westerners believe in it, we believe in it. That's what our education is. So Ganita, we saw in the Shukla Sutra, admits that its knowledge is non-eternal and imperfect. So practical value, not a practical value. So mathematics involves other religious delusions. These are not the only two religious delusions. That is why I told you my book. For example, the post-crusade Christian theology of reason, put forward by Aquinas, maintained that reason binds God. He cannot create an unreasonable world, he cannot create an illogical world, but he is free to create facts of his choice. Since logic binds God, God is free to create facts, therefore logical proofs are stronger than factual proofs. Who says so? I think factual proofs are stronger, always stronger. Metaphysics not to be trusted. But anyway, this was the belief. The deductive proofs or deduction is much more powerful, much stronger. It's completely wrong. Ganita accepts empirical proofs all the way from Shukla Sutra to Aryabhata, you will find empirical proofs being given. And let me also tell you, by the way, that there are no deductive proofs in the elements of Euclid, so called. There was not a single deductive proof of the Pythagorean theorem, so called, until the 20th century, when Russell and Hilbert proved it by assuming something similar, which is a trivial enterprise. Because you can prove anything as a theorem by assuming their property. So there wasn't such a thing. It's a total story, a quip, which nobody has checked, which you should check by just looking at the book. Just look at the book. This was acknowledged only after 800 years in the 20th century. That was the beginning of formal mathematics, trying to save the story, trying to save the myth, which is so important. So metaphysical proofs are more valuable. The first proposition of Euclid's elements, so called, is wrongly believed to be a valid deductive proof. It is not. It's a simple thing. Says, yes, I have a marker. So you want to erect equilateral triangle on a segment. So you have a segment. Markers are working. Yes, I see. Okay, right, thank you. So you have a segment, you draw one arc like that, and then you draw another arc and then join. Okay? How can this be a deductive proof? You see that the arcs are intersecting. But which axiom does it come from? No axiom which says they will intersect. It requires at least this so-called real number system. Because if I have something less, if I have some discrete number system, these two arcs will pass through each other without intersecting, without having any point of contact. Discussed in the previous engineers. So there was no valid proof. Then, simple thing, reason depends upon logic. What you are talking about, formal mathematics assumes two variables. Universal, it finds God, it's universal. How do you know it finds God? He visited God, popped out and came and told us. Right? What? How do we believe these kinds of things? So Indian tradition has so many different logics. Pre-Buddhist tradition and so many logics. You hear of Sanjay Belatiput and so on. Sanjay the skeptic and things like that. They describe in the Buddhist literature. You find it in the Brahmajal Sutta. There is Buddhist Chatushkoti, there is Jain Syarpad and so on. There is also two-valued logic in the Nyaya tradition. Which logic gives us? Logic is not universal. How can reason be? That is why Buddhists and Naiyayikas fought 2000 years, debated for 2000 years. They did not kill each other, but could not reach it. Newton accepted all these Western religious dogmas. He said mathematics has to be perfect because why God? That's what Aquinas said. God made He rules the world with laws of nature. That is why you call them Newton's laws. And those laws are eternal. Because they are eternal, they are written in the eternal language of mathematics. Believed all that. So he said, his mathematics must be perfect. Of course, he dismissed Darwinism. Darwin's second inventor of calculus didn't even understand he needed help. That's right. But he also was the second inventor who did not understand the calculus. That part nobody has said. So he wanted to use d by dt for his laws. And how to define d by dt perfectly? So he defined it as a fluxion. It's a very confused definition which has been abandoned. But the idea was what? That you can get perfection only through metaphysics. And his physics failed because in order to make his d by dt perfect, he made time metaphysical, absolute, true, mathematical time, which flows on without regard to anything external. That is what he states in his negate. And so many adjectives all say that it is metaphysical. Physics failed for that reason because it did not define a measure of time, did not define what a proper clock is. And precisely that he was trying to make calculus perfect, and he ended up making his own physical theory imperfect. Discussed in my book some detail. Time towards a consistent theory should be there in the library, I think. So today we abandon Newton's fluxion. We still use limits, not any less confused. Well, now I know how time goes. That's a separate thing, interesting thing. So the belief is that it requires real numbers for the existence of limits. That's what we teach. That's what I also taught once upon a time. So we teach in the school text that you require limits, you require real numbers for the calculus. You don't actually teach real numbers. How many of you learned real numbers? You learned real numbers. Okay. So there are 5. Did you also learn the set theory that is needed for it? Axiomatic set theory? Not knight set theory, not almost knight set theory. Axiomatic set theory. You didn't learn. So you learn one part, you don't learn the other part, it's all on trust, and that is the basis of perfect knowledge. There's a problem, no? So most people do not learn real numbers, then they learn calculus. All of you must have done calculus, this Institute of Science. All of you must have done mathematics. Am I right?
Yes.
Yes, so all of you have done it, but only a few have learned real numbers, and out of that few, nobody has learned axiomatic set theory needed to set up real numbers. That's the state of knowledge, that's a problem. So, most applications of calculus for all practical purposes do not require formal real numbers. How do I do it if I want to send a spacecraft? I compute its trajectory using a computer. And if I do it in a computer cannot use formal real numbers. So this is just, we are numerically solving a differential equation, which is just the way Aryabhata did it. More sophisticated, Runge-Gupta method or something like that. Doesn't matter. In principle, the same thing. One theory is that computers cannot ever use formal reals. They use floating point numbers. It's a completely different mathematical system. Because it does not, for example, obey floating point numbers, don't obey, for example, the associative law. It's different algebraically, different analytically, different in every way. And it's good enough for all practical purposes. Why do you need real numbers? Why do you want to teach real numbers? You can get along in life perfectly well without them. Why do you confuse people like that? That there is something which you don't know, which is very critical to this theory of limits. Then it is not adequate. It is not needed, that's another thing. It's not adequate. So if you use it, what happens? Must have learned every differentiable function is continuous. Therefore, a discontinuous function cannot be differentiated. But even before the calculus was formalized, with the formalization of real numbers, with the formalization of set theory in the 1930s, we were using, they were differentiating discontinuous functions. Hillside was doing it, Dirac was doing it. Today it is done using the Schwartz theory of distributions. But that theory is not good enough. So, for example, if you are shock wave, you must be doing some of you. So, shock waves arise very easily. That's a discontinuity. Now, after discontinuity, what happens to my differential equations of fluid flow? Maybe in the case of the air, you can say I'll go back to statistical mechanics and do some those fine equation, etc., etc. What do you do in the case of general theory of relativity? You have a continuum, you don't have any discrete basis, you don't have any statistical basis to the continuum, so you have to work with that discontinuum. What do you do there? You can't make any sense out of it because the equations are non-linear. And with non-linear equations, you have to multiply Schwartz distribution, which you can't do because it's a linear theory. There are theories which allow you to do that. Similar problem of multiplying distributions arises in the renormalization problem of quantum field theory. You have your propagators, the fundamental solutions of the equations, and you multiply them in the S matrix expansion. So they could be handled. In fact, I did handle them when I did my PhD thesis, when I didn't know anything, and I believed all this, then I used non-standard analysis to do that. And empirical input, that's the point. You cannot get away from empirical inputs. Just non-standard analysis is not going to give you a solution. Because when you multiply, for example, there will be a failure of the associative law. How do you fix the association of factors? It's a very tricky issue. Riemann tripped up on this theory of shockwave because of that. He thought that conservation of energy, momentum and mass, the same thing as conservation of mass, momentum and entropy. So equivalent equations give you inequivalent answers. But what do you need? You don't need non-standard analysis. All that you need is what is called non-Archimedean arithmetic, where you have infinities and infinitesimals. Any so-called ordered field larger, formally speaking, any ordered field larger than the real numbers will be non-Archimedean, because this is a characteristic property of the real numbers according to this. Therefore, it will have infinities and infinitesimals. And then you don't have limits. You have to discard infinitesimals. So 1 by n, you say when n becomes infinite, you get infinitesimal, but you don't have a limit as 0. So you have to discard infinitesimals. And that corresponds to limits by order counting when the formal limits exist, and this is discussed in my book, Cultural Foundations. But this process of discarding requires a different philosophy from formalism, requires a philosophy of zeroism, what I call zeroism. I have an article on that, so maybe you take a look at it, you take a look at that. What I want to explain is how this relates to Indian tradition. How Indians did that calculus, how they work with limits which all these historians don't understand. They go on talking nonsense. Like they talk nonsense about the Kamal for 2 centuries. That instrument which Vasco da Gama brought here, they did not understand it because it uses 2 harmonic scales. Applies the Vernier principle, so-called, Vernier didn't do anything, just copy. Applies that to harmonic scales, not linear scales as you do. So any innovation, go for a toss. So here there was non-Archimedean arithmetic. Why? Because Brahmagupta, introduced polynomials. So polynomial is something called abacus. So it's an abacus number. If you have something 3x plus 2, 2x plus 3, it acquires a value only when you give a value to x, so it's not expressed. Then when you take ratios of these fractions, then you say, well, this is unexpressed fraction. Naturally. What are these ratios? They are today what you would call rational functions, and they constitute what we call a non-Archimedean ordered field. That is how the limits were calculated. So-called limits, there were no limits. But the sum of an infinite series was calculated like that. So apart from all those differences of philosophy, that you are looking at empirical proof, you are not deductive proof, that you are looking at where you are making a calculation and so on, you make the calculation like this. And not by postulating real numbers and things like that. Very simple, intuitive way of doing things. So this is how we led to the sum of the infinite geometric series and to various techniques of accelerating convergence and so on of the Latin. So I will just talk a little bit, just mention what is the advantage already to work with Ganita, calculus as Ganita and not mathematics, what will happen. So one of the things is that you get paradigm shift, that if you have rejected Newton in physics, now you get functional differential equations, as I have been talking about. I have written a series of articles on this in last few issues of physics education, maybe last 2-3 years. Get a new theory of gravitation, because if you correct Newton in physics, you must also correct gravitation. General theory is overkill, which doesn't allow you to solve even the two-body problem. Doesn't certainly work for the galaxy. Newton in physics failed for galaxy, as we know, and we talk about dark matter. It works alright for the planetary system from which it was back. So this retarded gravitation theory allows you to do a many-body problem and can work whether for the solar system or the galaxy. It's possible. Leads to a modified electrodynamics using that theory of multiplying things and so on. So you could see some of these expository articles in physics education. Math better. Second thing is, so this is that it leads you to a better science. This is the claim I am demonstrating here. And the second thing is that it makes math teaching easy. So many people drop out because they are frightened of math. You are not one of them. You are the courageous people who survive. to survive. But you know there are so many of your colleagues who dropped out who hate math, who find it difficult. So, the theory is on the principle that phylogeny and ontogeny, the way the subject developed in Europe, they encountered many difficulties. Those difficulties are reflected in fast-forward mode in the classroom. And just as a growing child goes through all the phases of the evolution of the species, first is in water and then crawls on all fours and then stands up and so on. That's the idea. So those difficulties of Europeans that Europeans encountered are played in fast-forward mode. And it's all the metaphysics that they develop, which makes 2 plus 2 equal to 4. If you want to prove it, it makes 378 pages. So you don't want to do that. Most people are able to live their life without learning that proof of 378 pages. And if you learn it, it will not enlighten you. So the solution is to go back to the way it developed, reject it. And teaching calculus, the way it developed in India, makes it extremely easy. What did Aryabhata use? Rule of 3. They make it more sophisticated at a later stage. That's not a problem. But that's not what is taught in university calculus courses. They don't teach sophisticated numerical techniques. That's a separate course. So university calculus, everything that you do, you can solve about solving differential equations. All the applications to physics are about solving differential equations. So you solve differential equations, and that's what calculus is about. It's not about formulae for integration and differentiation, which are of no use. Worth nothing, because today maxima, faculty like maxima can do all that integration and differentiation for free, much faster than you can do. It's just a ritual. What you want to do is actually solve differential equation. And so you can replace that entire fat book on calculus which does all those techniques. 1300 pages, 2 columns, fine print, with an attached CD, which you can use. So you can teach it in 5 days, and I have demonstrated this with 8 groups in 5 universities in 3 countries. I reported it. So this is one group where I started like the bull from Sarnath. It's in Kutch, Sarnath. This is in Tehran. There were 4 groups in University of Science Malaysia. This is in Ambedkar University, Delhi. University of Science Malaysia, there were 4 groups. There were undergraduates in mathematics, undergraduates in applied mathematics, undergraduates in pure mathematics, and students of social science. Non-mathematics. So that's the conclusion that I would like to get to. That calculus developed in India as Ganita for its practical value. It was transmitted to Europe also for its practical value. It was not understood there, just as Indian trigonometry and arithmetic was not understood. It was changed to metaphysical math. And that inferior understanding was passed on to us, and glad to say for 2 centuries we have uncritically accepted it as a matter of blind belief. We need to give up that. We need to have a debate. Let us have a debate. I am standing here, I had a debate with Mukunda some point of time. He stuck to just the history of physics in the 1930s. He didn't come to grips with any of these claims that were being made. So I would suggest that we have debates on it, because this is what academics is about, not about publishing papers, but let's have a debate where things are transparent, people engage with it. So it is still being taught today. We need to get rid of it. We should change that false history. If we don't change it, just cross-check it. Don't believe Wikipedia. Don't believe the secondary sources that it cites. Go to the primary source. Ask, does the primary source exist? Whether for Euclid or for Archimedes or for Pythagoras or for Ptolemy and so on. Claudius Ptolemy, and then we need to debate these things publicly. Rest is notorious for false history. See, the church has been saying false history is our province, and they have been using it to be used for the benefit for the last 1700 years. It's not only some Hindutva people here who do it. This has been going on, and the right answer to that is not to have one's own false history, but to explore that false history and say let's have history based on evidence. This is very important. So we should believe that India had something to offer, something solid to offer, which will withstand any kind of scrutiny for the evidence. We just talked about it. So many other things. So it will withstand the scrutiny, so you don't need any false claims. Let us stick to realistic claims, and let us also make the West stick to these realistic claims. So much of false history they have come up with. So that's the idea, and then that claim of false history was used to claim superiority and colonial superiority, racist superiority, and then those claims of Christian superiority earlier. Vasco discovered India. I was a child, I asked, where were we? Were we here or were we somewhere else? The idea is that non-Christian don't come. That is what they did, doctrine of Christian discovery in the United States, or in North America, South America, it's so pathetic. Anyway, the point is that there is religious metaphysics which we don't need. What we need is a practical value. Let's have the practical value. And if something else comes up from there, let's have that. That's fine. But we should eliminate that religiously loaded metaphysics, which has hindered science, as I pointed out, and made math difficult. Why do we want to do that? We should teach practical and secular running, not religiously loaded metaphysics, especially in schools, because in schools, math is a compulsory subject. Why do you want to teach piano axioms and associative law and things like that? Especially since India is a secular country. Thank you very much.